When two or more vectors are acting at one particular point, their net effect or net outcome will be the algebraic sum of their individual vectors. When sound waves was actually passing through the air, he assumed that, okay, since sound wave is passing too quickly, there is no change in temperature. Particles which are situated at specific points will not be moving, and that particular point is known as nodes, and the points which have maximum displacement is known as antinodes. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to discuss the remaining portion of the chapter, that is waves. So let's see what waves hold for us today. So in the last session, I told you the general equations to find the speed of a wave in any particular medium. Now we are going to specifically discuss the speed of a wave in a gaseous medium, and that was found by Sir Isaac Newton. So Isaac Newton actually calculated the speed of sound, and surprisingly he was wrong and he was off the value by a lot. So again, Laplace, another scientist, came in and fixed that particular error. So we are going to see Newton's equation for speed of a wave in gas and again Laplace's correction. So first let's start with Newton's assumptions, or simply Newton's derivation. So again, for this, the idea Newton took, or the consideration he took, was that when sound waves was actually passing through the air, he assumed that, okay, since sound wave is passing too quickly, there is no change in temperature, which means that sound wave, as it passes through, the energy will change, but the temperature will remain constant. That is, he thought that sound waves while traveling through the air will be an isothermal process. This was his apparent mistake, but he didn't know that at the time, and he started the equation saying that, okay, if that is true, then this will be equal to a constant, that is PV is equal to a constant value. Now, if I take the derivative of this on both sides, that is taking derivative, I can say that again here, since it is two products being multiplied, I have to apply the product rule. So again, the product rule states that first quantity into derivative of the second plus second quantity into derivative of the first. That is how the product rule works. You'll study it in detail in your second PUC. So first quantity into derivative of the second. So I'm just using delta here to signify or simply represent the derivative that is taken here. So first quantity into derivative of the second plus second quantity into derivative of the first will be equal to 0, because derivative of a constant will always be equal to 0. So rearranging this particular equation, that is P delta V will be equal to minus V delta P. Now, if I take this delta V also to the other side, then I have an equation in terms of P, which is minus V delta P divided by delta V. So what is this V delta P divided by delta V? Again, if you remember your chapter on mechanical properties of solids and fluids, you will understand that this particular equation is vaguely similar to an equation you already know. So again, if you see closely here, V delta P by delta V is nothing but bulk modulus. That is, this entire quantity is nothing but bulk modulus, which means that here we can substitute the term, that is B. So we have an equation under this condition, P is equal to B, which is nothing but bulk modulus. So again, previously we have stated that, okay, in a gaseous medium, the velocity of a wave will be equal to root of B divided by rho, right? Root of B divided by rho. Since B is equal to P in this particular case, we can rewrite this equation as B is equal to root of P by rho. This was the famous assumption that Newton got wrong. So the speed of a wave will be equal to root of p by rho. But the problem was again that when he calculated the value of this particular velocity, that is when he calculated the particular values at STP, that is standard temperature and pressure, he found that the velocity value was approximately 280 meter per second. And already you know that this is not the velocity of sound in air or simply in any gaseous medium. The velocity of sound in air is actually 330. That is in between 330 and 340, but more precisely we learned that it is 332 or 31 meter per second. So comparatively, this reading is much off. It is off by a factor of 50 or more. So that is why Newton was actually wrong. So where did Newton actually go wrong? That is where Laplace came in and made the correction. So Laplace said that, okay, Newton got it wrong, and he said that, okay, this is only because he considered this to be an isothermal process, while in actuality, it is nothing but an adiabatic process. So instead of PV is equal to a constant, you have to take PV raised to gamma is equal to a constant. Why? Because it is an adiabatic process, and an equation for the adiabatic process is again PV raised to gamma is equal to a constant, or P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So that is for an adiabatic process. So Laplace said that since the wave is moving too fast, there is no time to have change in energy. So we say that PV raised to gamma is equal to a constant. That is, it is an adiabatic process. No energy exchange is taking place in the process of a sound wave, or simply when sound is traveling through air. So again, using this assumption, we are going to do the same technique, that is taking derivative on both sides. Again, one thing you have to know here is that it is not PV, it is PV raised to gamma. So when you derive, that is when you derive x raised to n, take the derivative of x raised to n, then there is one small problem. You cannot take direct derivative of that. The result you will study again in your second PUC, but the result will be n x raised to n minus 1. This will be the result, which means if I take the derivative of v raised to gamma, it should be gamma into v raised to gamma minus 1. So we have to apply that particular result here, and along with that we also have to apply product rule because it is two products. So again, first into derivative of the second. So derivative of the second will be equal to gamma into v raised to gamma minus 1, and we also have to take the derivative of v. So delta v plus second function into, that is v raised to gamma into delta p is equal to 0. Now again what I'm going to do is that divide this entire equation throughout by v raised to gamma minus 1, because I don't want this term to be here. So I'm going to divide throughout this equation by v raised to gamma minus 1, which means that it will be p gamma v raised to gamma minus 1 delta v plus v raised to gamma delta p, right? And I'm going to divide this side, all with v raised to gamma minus 1, v raised to gamma minus 1. You can either take it together, but it will be much more easier if you take like this and explain how the cancellation process happens. So again, there is v raised to gamma minus 1 here, v raised to gamma minus 1 here. So these both get cancelled out. Now in this stage, I am going to write it as v raised to gamma, that is this particular equation v raised to gamma minus 1 can be written down as v raised to gamma into v raised to minus 1. A raised to m into a raised to n is equal to a raised to m plus n, which means v raised to gamma into v raised to minus 1 will be equal to v raised to gamma minus 1. And v raised to minus 1 is nothing but 1 by v. So again, this v raised to gamma and this v raised to gamma will cancel out, and the only thing remaining will be a v. I'll write it here. So here it will be p into gamma into delta v plus v raised to gamma delta p divided by v raised to gamma into v raised to minus 1. V raised to gamma and v raised to gamma cancels out, and v raised to minus 1 is nothing but 1 by v, which will go to the numerator. So I can write this as p into gamma into delta v plus v delta p will be equal to 0. Now again the same process I'll do again, that is I'm going to take v delta p to the other side. So I can write it as p gamma delta v is equal to minus v delta p. Now again taking these to the left hand side, I can say that p into gamma is equal to minus v delta p divided by delta v. So again, this particular equation, we already know that it is nothing but bulk modulus B. And velocity of a gas is given by the equation root of B by rho, which means that instead of B, I can substitute P gamma. So instead of this, I can also write it as P gamma divided by rho will be equal to the velocity. So again, we have one more expression, that is Laplace's correction for Newton's error, and that is given by P gamma divided by rho. So it is not an isothermal process, rather it is an adiabatic process. So again, how did he know he was correct? Because when he calculated the value at STP, now the value came out to be, the velocity value came out to be 330 meter per second. So according to Newton, it was around 280, but now it is more than 300, which means that there was a significant error to be reduced, which was done by Laplace's correction. And experimentally in later stages, we found that yes, it is in between 330 and 340 meter per second, which means that Laplace was actually correct. So the next thing you have to learn is nothing but superposition of waves, or simply the superposition principle for waves. So what exactly is superposition principle? So as you know that we cannot add vector quantities just like we do for scalar quantities. So we have the superposition rules. That is, when two or more vectors are acting at one particular point, their net effect or net outcome will be the algebraic sum of their individual vectors. Or in the case of waves, we can actually define it as when two or more waves pass through a particular point. That is, if one wave is coming like this and another wave is coming like this, what is the net output? We need to calculate what is the net output. If this is wave 1 and this is wave 2, then what is the net output of that particular wave? So that can only be mathematically calculated using the superposition principle. So it states that when two or more waves pass through a particular point, then the net displacement will be equal to the algebraic sum of the displacements of the individual waves. So y will be equal to y1 plus y2. And y is nothing but the wave equation which you have already learned. That is nothing but a sine kx plus or minus omega t plus phi. So that will be substituted here. If you ever wanted to find what is the displacement of two or more waves that is passing through a particular point in a given medium. So the next topic you have to know is something known as stationary waves or standing waves. So what exactly is a stationary wave or a standing wave? So when there are two waves which are traveling in the opposite direction and they nearly have the same amplitude, frequency and speed in that particular given medium, then they will interact with each other and the lows and highs will be cancelled out and they will have a steady state of flow. So when they have that steady state of flow, when they achieve this particular balance, a new wave emerges and that particular wave is known as a standing wave. That is, when two or more waves are in mix in particular medium, that is, two or more waves are interacting in a particular medium which is having almost the same amplitude, frequency and all that, then they will cancel their highs and lows and they will produce a new wave which is very steady in that particular medium. So if I have two rigid support like this and the pink wave is going in the x direction and the blue wave is coming in the negative x direction, then I can say that both of them after some time will have a steady state where they will interpose with each other. That is, they will superimpose on each other and a net displacement or simply a new wave will be produced, and that wave will be steady and stationary, which means that only amplitude will change and there won't be any displacement in any particular direction. So that kind of wave is known as a standing wave or simply a stationary wave, which means that if I keep a particle here or here, the amplitude will change, which means that displacement will be there for these particles only in the up and down direction. But particles which are here on the red dots will never be moving. They will always be in a position of rest or in a state of rest. So based on this, we can actually say that, okay, particles that is on the amplitude of the wave will be having maximum displacement, which means that they will be moving up and down. But particles which are situated at specific points will not be moving. And that particular point is known as nodes, and the points which have maximum displacement is known as antinodes. So these particular red dots will be called as nodes, and these other ones which will be having maximum displacement is known as antinodes. So you have nodes and antinodes. So again, nodes are simply positions at which the amplitude of the vibration of the particle is zero, basically meaning that they will be at rest. And antinode is nothing but the position at which the amplitude of vibration of the particle is maximum, which means they are free to move up and down to maximum amplitude. That is, maximum displacement will be produced. So again, if the conditions are right in a closed container or in a set boundary, you can actually produce what is known as a standing wave. So again, the next thing you need to know is the equation for a standing wave, and only after that can we go into the further principles, applications and examples of these particular standing waves. So what exactly is the equation of a standing wave? Again, we only need to apply the superposition principle, that is, so again, we need to consider two waves which are traveling in the opposite direction, which means that y1 will be given by a sine kx minus omega t and y2 will be given by a sine kx plus omega t, which means one wave is traveling in the negative direction and one wave is traveling in the positive direction, because here it is minus and here it is plus, just like we discussed in the last session. So again, they need to produce standing waves, and that will only happen when they will superimpose on each other, which means we have to apply the superposition principle, which states that the net displacement will be equal to y1 plus y2. Again, y1 plus y2 means that it will be equal to a sine kx minus omega t plus a sine kx plus omega t. we need to add them together. So again, you can see that A is common here. We can take the A outside. Then we can write it as A into sine kx minus omega t plus A sine kx plus omega t. So again, you have an equation where this is of the form, this is again of the form sine A plus sine B. So again, if you remember your trigonometric functions, you would identify instantly that sine A plus sine B is nothing but 2 sine A plus B by 2 into cos A minus B by 2. So we are going to apply that particular result so that we have an equation for this. So we know that sine A plus sine B will be equal to 2 sine A plus B by 2 into cos A minus B divided by 2. So when we apply this particular result, we'll get the net output, which means that instead of A and B, we have kx plus omega t and kx minus omega t. So we can write it as 2 sine kx plus omega t plus kx minus omega t whole divided by 2 into cos kx plus omega t minus kx minus omega t. So again, whole divided by 2. So when we apply this particular result, what will be the net output we are getting? So again, here when we open the bracket, omega t and minus omega t will cancel each other out. And here when we open the bracket, kx and minus kx will cancel each other out, which means that here it will be 2 kx and here it will be 2 omega t divided by 2 divided by 2. And don't forget, there is an a also here. That is the amplitude which is not part of this particular result, but there is a constant a in the equation we applied. So we have to apply it here also. So this will be equal to 2a into sine 2kx divided by 2, 2 cancels, into cos 2 omega t divided by 2, so that also cancels. So again, in the final result, we have 2a sine kx cos omega t. Now, again, if I take this particular term all together, then I can say that is 2 sine kx. So 2 sine kx, if I'm taking all together, I can say that, okay, this is the net amplitude of the wave. It is the net amplitude of the wave, and this is the nature of the wave. So again, if that is the case, then I can predict where the nodes and antinodes are going to appear. Again, antinodes means it is the maximum displacement and nodes means it is the minimum displacement. So we can predict where it is going to be maximum and minimum. We just need to know where sine is 0 and where it is maximum. So again, where it is 0, there will be nodes, and where it is maximum, it will have antinodes. So again, sine kx, sine will be 0 only in the even multiples of pi, which means pi, 2 pi, 3 pi, 4 pi, like that. Sine will be 0, and in the odd multiples, it will be maximum value, which means that we can equate sine kx to, or simply kx to n pi. That is 2a sine kx to be 0 implies that sine kx should be 0, implies that kx should be equal to n pi. So again, which means that this term should be a multiple, even multiple of pi. So n is 1, 2, 3, 4, like that. So for this term to be 0, that is sine term to be 0, kx should be equal to a multiple of pi, that is a whole multiple, 1, 2, 3, like that, not irrationals. So again, we know a substitution for k, that is, we know that k is equal to 2 pi divided by lambda, because k is the wave number or wave constant, and wave constant is given by the equation 2 pi by lambda. So we can substitute that here, and then we can write it as 2 pi divided by lambda into x is equal to n pi, which means pi and pi will cancel each other out, and we have x is equal to n lambda by 2. So we have an equation for displacement that is n lambda divided by 2. Now again, this is the case for nodes, where the waves will be having zero displacement. Now what about maximum displacement, that is antinodes? For antinodes or maximum displacement, 2a sine kx should be equal to 2n plus 1 into pi by 2. So again we can say that kx should be equal to 2n plus 1 into pi divided by 2. Again k, we are substituting the value, that is 2 pi divided by lambda into x is equal to 2n plus 1 into pi divided by 2. Again pi and pi cancels out. If I am taking this there, then we can write it as x is equal to n plus 1 to n plus 1 lambda divided by 4. So again, all the odd multiples of lambda by 4, we will be having antinodes, and all the even multiples we will be getting nodes. So again, the next thing is that standing waves on a stretched out string. That is, if you have a guitar, then you can imagine a guitar. If you don't have a guitar, imagine an ukulele. Whatever you want to imagine, just imagine a string which is tied in between two rigid support, and then when it is struck, when the string is struck, certain waves are actually produced. So these particular waves that are produced are actually in some definite patterns. You cannot break the pattern, and what it means is that every time you pluck a string that is in between two rigid support, there are certain mathematically predictable definite patterns that arises. And these particular mathematical patterns are known as normal modes. That is, there are a set number of vibrations that is possible in between that particular rigid supports, and that particular pattern is known as normal modes, and that is determined by the frequency of the wave that is traveling through that particular string. So these are some of the definite patterns you need to know. So these will be derived here, that is the definite patterns, or simply the normal modes will be derived, and you will find the relation between these three normal modes. So the first thing you need to know is that when we are finding out the first normal mode, or simply the first mode, imagine that there are two rigid supports separated by a distance of L, and the waveform you obtain is like this. When you stretch out a string and you pull the string, you have this maximum displacement up and down, and the shape is like that of an eye. So you have this particular shape, and we are going to derive a mathematical relation or simply find out what is the frequency of that particular wave that is formed. So again, you do know that displacement, that is displacement divided by time, is nothing but velocity. So you know that displacement by time is velocity. Here, what is the displacement? So displacement is, again, it is linear displacement which is expressed in wavelengths, and here the displacement is nothing but through a distance of L. So we can say that L is the distance that is being traveled. Now, what is the time taken? That is time period. So time period will be T. But it is distance by time, which means 1 by T. 1 by T is nothing but mu. So 1 by T can be expressed as mu, that is frequency. So since that is clear, let's see how much the wave has actually traveled. So when the wave has traveled one cycle, we say that, okay, it has completed 1 lambda distance. But in this particular case, there is not one full cycle, but rather it is only a half cycle. There is only 1 half here, which means that the wave has only completed half the distance or half the cycle, which means that the distance that it traveled is actually equal to lambda by 2. So for the first mode, it only traveled the distance of lambda by 2. So it only traveled the distance of lambda by 2, and lambda, which is nothing but displacement of a wave, will be equal to V by mu. That is because displacement is equal to velocity into time, but here it is velocity and time period. Time period is nothing but inverse of frequency, so velocity into 1 by frequency, that is mu raised to minus 1, or simply V by mu will be the answer for displacement. Here displacement is lambda, so that is where we get the form lambda is equal to V by mu. So again, we have the equation lambda is equal to V by mu. When we substitute that here, we have an equation that can be written down as L is equal to V by 2 mu. So if I shift these together, then I can say that mu, that is the first frequency, will be equal to V by 2L. So V is the velocity of the wave, mu is the frequency, and L is the distance between the two rigid supports. So you have the first mode as mu1 is equal to V by 2L. Similarly, for the second mode, we can say that the length, or simply the distance it traveled, is actually here again lambda by 2, lambda by 2. So it traveled half and half, which means one entire cycle, which means lambda. But I'm going to write it in the sense, instead of lambda, I'm going to write it as 2 lambda divided by 2. Right? Lambda by 2, that is 1. This is 2 lambda by 2. Again, it is nothing but lambda, but I'm going to write it like this because there will be a relation between these three modes. So in order to understand that, I'm just going to keep it like this. So again, the same procedure, lambda is equal to V divided by mu, which means that I can substitute here L is equal to 2. Instead of lambda, we have V by mu, and here also there is a 2. So 2V divided by 2 mu. Exchanging, we have mu 2 is equal to 2V divided by 2L. Now, why I kept the 2 is because here see, if I take just this term, it is mu1. So I can say that mu2 will be equal to, that is second frequency will be equal to 2 times first frequency. So second frequency will be equal to 2 times the first frequency. And similarly, we can also prove for the third wave, and the third normal mode will be proven as, mu3 will be equal to 3 times mu1. That is because here it is lambda by 2 lambda by 2 and lambda by 2, which means 1 lambda by 2, 2 lambda by 2, 3 lambda by 2. So instead of 2 lambda divided by 2, we'll have 3 lambda divided by 2. So here it will be, instead of 3 lambda, we can write it as 3v divided by 2 mu. So it will be ultimately equal to mu3 is equal to 3 mu1. So again, mu3 will be equal to 3 mu1. That will be the final result for the third mode. So we have mu1, mu2 and mu3. And these are called in a specific way. This one is known as the first harmonic. Is known as the first harmonic or the fundamental frequency, since it is the most basic one. This one is known as second harmonic, also known as the first overtone. First overtone. And similarly, this one is the third harmonic and also known as the second overtone. So that is all about normal modes, that is mode 1, mode 2 and mode 3 on a stretched out string. Now what about in the case of a closed pipe? Imagine that this is a closed pipe and let's say one end is filled with water, or it is simply closed like a flute. The flute is closed in one end and open at the other end. Just like that, or like a bottle, like one end is closed and the other end is open. So the vibrations or the nature of the waves that is formed in those pipes will also be in a certain set pattern. So we are going to find whatever we did in the previous derivation, same thing we are going to do again. So again, this is the first node, this is the second node, and this is the third node. So we have first mode, second mode and third mode. So we have first mode as L is equal to, now how much wavelength is it covering? So again, instead of writing like this, it is being written like this, which means that this is one wave. This is one wave. And here we don't have one wave. Instead, we only have quarter of a wave. That is, we only have this bit here. It is like this. Only we have this bit. If we had one entire eye, we can say that that will be half lambda. But we only have half of an eye, which means quarter of a wave. So this is only lambda by 4, quarter of a wave, which means that up to here is only present. So up to here, here and here. Like that, we can divide the waves into sets of lambda by 4. Here it is only lambda by 4. And if it moved here, if it connected here, that will be half lambda, and it went back, then it will be 1 lambda. So here it is only lambda by 4, which means that here L is equal to lambda by 4, which means that when we write it down in terms of mu or simply V and mu, we can say that it will be V divided by 4 mu, which is equal to L, or simply mu1 is equal to V divided by 4L, which is known as the first harmonic or fundamental frequency. Right. Now, in the case of the second mode, similarly, how many waves do we have? We have lambda by 4 here, 2 lambda by 4 here, and finally we have 3 lambda by 4 here, which means that L here is equal to 3 lambda divided by 4. And again, applying this particular equation, we have L is equal to 3V divided by 4 mu. So again, we can write it as mu is equal to 3V divided by 4L. And again, V by 4L is nothing but mu1. So we can write it as mu2 will be equal to 3 times mu1. 3 times mu1. And again, for the last mode, that is the third mode, similarly we can prove that how many waves are there? There is lambda by 4, 2 lambda by 4, 3 lambda by 4, 4 lambda by 4 and 5 lambda by 4, which means here L will be equal to 5 lambda divided by 4. And again, rewriting this equation, L is equal to 5V divided by 4 mu. Rearranging, we have mu is equal to 5V divided by 4L, and V by 4L is nothing but, that is V by 4L is nothing but mu1. So I can write it down as mu3 is equal to 5 times mu1. So we have the equation as mu3 is equal to 5 times mu1, mu2 is equal to 3 times mu1. So if I take the ratio of first mode is to second mode is to third mode, that is first mode is to second mode is to third mode, I will be getting the ratios as 1 is to 3 is to 5. That is only odd numbers are present. In the previous case, that is on a stretch string, if I take the same ratio, I'll be getting the ratio as 1 is to 2 is to 3. Mu1 is to mu2 is to mu3 will be equal to 1 is to 2 is to 3, which means it is a natural number progressing just like that. But in the case of a closed pipe where it is opened at one end and closed at the other end, we have the ratios to be purely odd number in nature. That is, we have the ratio as 1 is to 3 is to 5. Since we discussed about a stretch string and one end open pipe where the other end is closed, we now have to discuss about a pipe where both ends are completely open. So we are going to discuss that also here. So in the same case, we are saying that, okay, this is first mode, this is first mode, this is second mode, and this is third mode. And we are going to find what are the harmonics, first harmonic, second harmonic, third harmonic. Similarly, first overtone, second overtone for this also. And again, remember, here it is the first harmonic, fundamental frequency. Here this is the second harmonic, that is the first overtone. And finally here it is the third harmonic and finally the second overtone. Just like that, we are going to find in the case of an open pipe also. So how much is this particular wavelength? Again, just calculate. So we know that this was lambda by 4 and that means lambda by 4 plus lambda by 4, that is lambda by 2. So this particular distance is nothing but lambda by 2. So we have for the first mode, we have L is equal to lambda by 2, which means that when we apply the equation, L is equal to V by 2 mu, or simply mu is equal to V divided by 2L. So this is first frequency, or simply the first fundamental frequency, also known as the first harmonic. And similarly for the second mode, we can say that L will be equal to, so here what will be the wavelength? Here it was lambda by 2. So here it is going to be lambda by 2 plus lambda by 2. So that is 2 lambda by 2. So 2 lambda divided by 2. So we can write it as lambda is equal to 2V divided by 2 mu. And again rearranging, we have mu2 is equal to 2V divided by 2L. So again mu2 is equal to 2 times mu1. And similarly for the third mode, we can similarly prove that mu3 will be equal to 3 times mu1. Why? Because here L will be equal to, from here to here it is lambda by 2, from here to here it is again lambda by 2, and here to here it is again lambda by 2, which means that you have lambda by 2 plus lambda by 2, that is lambda, plus lambda by 2, that is 3 lambda by 2. So when you derive that, we have the relation as mu3 is equal to 3 mu1, that is known as the second overtone or the third harmonic. So we derived all three relations between frequencies, that is connecting open pipe, closed pipe and a semi-open pipe. And the last thing you have to learn in this particular chapter is something that is known as beats. I mean, you all know what beats is. It is the waxing and waning of sound. That is the sudden ups and lows of sound you suddenly hear when you are at a disco pub or you're hearing to loud music or your boomer or speaker or something like that. You can still hear through your woofers that sound is waxing and waning. That particular beat is known as beats. That happens when two or more waves interfere with each other. It produces highs and lows of sound waves. So these highs and lows, which is known as waxing and waning of sound, is called as beats. So again, we can define beats as when two or more waves, or simply two waves which are traveling in the same direction, which is having almost the same amplitude and nearly the same frequencies, when they are superimposed, when they are added together, then we'll have an output wave which will have intensities which are varying, that is increasing and decreasing in intensity. So these will produce beats, that is the waxing and waning of sound. And the frequencies of these particular waves are very easily found out, which will be equal to, beat frequency will be equal to mu1 minus mu2. But how do we know that it is mu1 minus mu2? That is first frequency minus second frequency. How do you know that? So again, we are going to apply the superposition principle. Y is equal to y1 plus y2, where y1, let y1 be equal to a sine omega 1t, and y2 let it be equal to a sine omega 2t. So I'm not taking kx or anything here, since the both waves are traveling in the same direction. I'm just taking the frequency, that is the angular frequency itself, and I'm not taking any other quantity. So when we do this, we'll have a relation, that is y will be equal to a into sine omega 1t plus sine omega 2t. So again, you have a trigonometric result which states that it will be equal to 2 sine a plus b by 2 into cos a minus b by 2. So again, we can apply that particular formula, and then we can write it down as a into 2 sine a plus b by 2 omega 1t plus omega 2t divided by 2. So omega 1t plus omega 2t divided by 2 into cos omega 1t minus omega 2t divided by 2, which can be written down as 2a into, I'm taking t also common right outside, and here also t is common, I'm taking it right outside. So, and I'm writing the cos term first, so it is cos omega 1 minus omega 2 into t into sine omega 1 plus omega 2 into t whole divided by 2 whole divided by 2. Now, in this particular equation, this 2a cos omega 1 minus omega 2 t divided by 2, I am taking this as amplitude. That is 2a. So when you multiply this 2a will be coming here. So 2a cos omega 1 minus omega 2 divided by 2 whole into t will be taken down as amplitude of this particular wave. So if that is amplitude, then we can definitely say that omega 1 minus omega 2 divided by 2 into t will be equal to maximum only when, that is, the amplitude will only be maximum when this particular term is 0. Again, if this term should be 0, then it should be the even multiples of pi, as cos will only be 0 at even multiples of pi. For example, then we can say that omega, which is equal to 2 pi mu, that is, angular frequency is related to linear frequency by the term 2 pi mu. So if I substitute that, I can write down as 2 pi mu1 minus 2 pi mu2 divided by 2 will be equal to, into t will be equal to n pi. Now if I take the pi common and the 2 common and cancel them out, you have mu1 minus mu2 into t is equal to n. So again, keeping the t here, if I take the mu1 minus mu2 to the other side, you have t is equal to n divided by mu1 minus mu2. So you have an expression like this. And again, if I take the time interval t2 minus t1 to be capital T, that is time period, then I can have an equation like this. T will be equal to t2 minus t1. So again, what this actually means is that you have an equation in terms of t, that is time taken, and you can say that t2 minus t1 will be equal to capital T. Then again, we can just simply see that t, which is equal to 1 by mu, implies that this can be written down as 1 by mu 1 minus 1 by mu 2, or simply 1 by t is equal to mu. And from that particular relation, you can just simply write it down as mu1 minus mu2. That is where you actually obtain the beat frequency from. But it is only important that you know beat frequency is mu1 minus mu2. With that, we are finishing our last chapter, that is known as waves. And I hope you have understood everything about the superposition principle. And that concludes our chapter waves. And I hope you have understood everything about waves in this particular class. I'll see you all very soon. Until then, thank you.